Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to cover material from your online Math 136 class at Ivy Tech for week 12. So we're going to start with section 6.4, which is all about logarithmic functions. So hopefully remember that a one-to-one function y equals f of x has an inverse function that is defined by the equation x equals f of y. And in particular, the exponential function y equals f of x, which is a to the x power, where a is greater than 0 and not equal to 1, is going to be one-to-one, and it's going to have an inverse that's defined implicitly by the equation x equals a to the y, where a is greater than 0 and not equal to 1. And this inverse function is so important that it's given its own name. It's the logarithmic function. So it's important to note that exponential and logarithmic functions are inverses of one another. So let's look at a definition for the logarithmic function to the base a, where a is greater than 0 and not equal to 1. We read it as y equals, or y is, the logarithm to the base a of x. Normally I just read it as log base a of x. And it's defined as the following: y equals log base a of x if and only if x equals a to the y power. Now, the domain of a logarithmic function is going to be all x's that are greater than 0. So if you try hitting the log button in your calculator followed by some negative number, your calculator is going to come up with some kind of domain error. So it's important to remember that we only have logs of positive numbers, okay? So x has to be greater than 0. And then these two things right here, these are equivalent, okay? So if you have y equals log base a of x, that means that x equals a to the y. I would go ahead and take a minute to go ahead and write these down because we're going to be using these a bunch of times. We have to switch between logarithmic and exponential forms several times in order to solve different types of equations or answer different types of questions. So I would go ahead and copy down what is in this red box here. Okay, so let's look at this example here. If y equals log base 3 of x, then x equals 3 to the y power. So it's important to note that all we've done is we've just rearranged this and we've written it as exponential instead of logarithmic. So for example, 4 equals log base 3 of 81 is equivalent to 81 equals 3 to the 4th power, which is true. You should know that 3 to the 4th power is 81 because 3 times 3 is going to give you 9, times another 9 will give you 81. Now if you have this right here, if y equals log base 5 of x, then again we can write it kind of the same way that we did for a. X equals 5 to the y power. So for example, if negative 1 equals log base 5 of 1/5, okay, so all we're doing is just plugging some numbers in here, that's equivalent to saying that 1/5 equals 5 to the negative 1 power. So we take whatever we're taking log of, which in this case was 1/5, and that now is by itself. And then our base remains our base, but it's our base for our exponent. And then whatever was by itself now becomes our exponent. So let's go ahead and practice actually changing exponential statements to logarithmic and the other way around. So let's say we have something like this here, 1.2 to the 3rd power equals m. And what we want to do is we want to change this exponential expression into a logarithmic expression that would be equivalent. And then down here, this is the thing that I had you write on your paper. It's important to kind of be able to visualize this and make sure that you either have this memorized or look to see if it's on your formula sheet. So if you have 1.2 to the 3rd power equals m, that looks like this right here. The m is actually the x, because that's the piece that's by itself. The a, which is your kind of base, is the 1.2, and then the power is the 3, okay? So if we take all of this apart and rewrite it in this form right here, we're going to have 3 equals, because it's whatever was our exponent, equals log base, and then the base is the 1.2, because that's the base for our exponent up here, and then it's of m. It's just the remaining piece. So the exponent now goes by itself. The base remains the base, but for the log instead of the exponent, and then the number that was by itself is now what you're taking log of. So if you have 1.2 cubed equals m, that's equivalent to saying 3 equals log base 1.2 of m. So I want to give you probably about a whole minute to see if you can figure out how to rewrite b and c, and then we're going to go through them. Okay, so hopefully you figured out at least part B, and then we're going to talk about C as well. So for this one, you have e to the b power equals 9. It looks very similar to this one here. So if we rewrite this, the b is the exponent, so it's now going to go by itself. So we have b equals, the base is this base here, so we have log base e, and then the number that was by itself is now what we're taking log of. So we have b equals log base e of 9. And then over here, we can rewrite this as 4 equals, because it's always the exponent, equals log base a, because the base is a here, of 24. Now we're going to do some the other way around. So we're given a logarithmic expression and we want to rewrite it so that it has an exponent here. So if we have log base a of 4 equals 5, what we notice is that our base is our a, and then our exponent should be the one that was by itself. So we have a to the 5th power equals 4, which is what's written right here. A to the 5th power equals 4. Let's do one more together and then I'll have you guys try part C on your own. So for this one, you're going to have e, that's your base, to this power right here. So you're going to have e to the negative 3rd power equals b. So it's your base raised to your exponent equals this number right here. So let me go ahead and give you about 30 seconds to try part C, see if you're able to rewrite that with a logarithm. Okay, so hopefully you figured out that this one is going to be 3, that's your base, to the c power equals 5. So now that we know how to switch between exponential and logarithmic, we're going to now learn how to evaluate logarithmic expressions. So let's find the exact value of some logarithmic expression here. Let's say we have log base 3 of 81, and we want to figure out what exactly this is. So what we're really asking is 3 raised to what power yields 81? And if you think about it, we could set up an equation that looks like this. Y equals log base 3 of 81, that's what we're trying to find. And if we rewrite this as an exponential, you're going to have 3, that's your base, to the y power equals 81. And if you think about that, 3 to the 4th power is 81. So you're just going to have y equals 4, or you're just going to get 4 as your answer, because 3 raised to the 4th power yields 81. Therefore, log base 3 of 81 equals 4. All right, let's take a look at part B as well. So this one we're asking 2 raised to what power yields 1/8. So we rewrite this as an equation again, just like we did last time. Y equals log base 2 of 1/8. And then we just rewrite this as exponential. So we have 2, that's our base, raised to the y power equals 1/8. And hopefully you can figure out that 1/8 we can rewrite as 1/2 to the 3rd power, since 2 cubed is 8. And hopefully you remember some of the stuff that we learned about exponents. If we have an exponent in our denominator, we can move it to our numerator if we make it negative. Okay, so this is going to be 2 to the negative third power. So we have 2 to the y equals 2 to the negative third. And since we have the same bases, we can ignore them. So we're just left with y equals negative 3. So that means that log base 2 of 1/8 is going to be negative 3. Okay, now we talked a little bit about the domain when we first introduced the logarithmic function, but let's solve some problems with that, okay? So hopefully you remember when we have inverses that the domain and the range flip-flop. So the domain of the logarithmic function is going to be the same as the range of an exponential, which is just 0 to infinity, not including 0. And then the range of a logarithmic function is going to be the same as the domain of an exponential, which in this case is just all real numbers. So domain of logs are going to be from 0 to infinity, not including 0, and the range of a logarithmic function is going to be all real numbers. So if we look right here, this is just a different notation. We have y equals log base a of x. The defining equation for that was x equals a to the y power, and the domain can be written like this, and the range could be written like this as well. Or you can write it in interval notation, which is how it was done up here. Okay, so let's work on actually finding the domain for some logarithmic functions. These are very typical types of problems, so it's important that you know how to solve these. So if you think about it, we know that whatever we're taking log of cannot be 0, and it cannot be negative. So what we actually need to do is we need to take whatever's in parentheses here and we need to set it greater than 0. So in this case, we need to set x minus 2 because that's what's in parentheses, and we need to set it greater than 0. So in order to solve this, if we just add 2 to both sides, you're going to get x is greater than 2. Or we could write this in interval notation from 2 to infinity. All right, now if we take a look at part B, this one looks a little trickier. We have an inequality. We have x plus 3 over x minus 1 is greater than 0. And hopefully you recall how to actually solve this. Okay, this is one of the ones, it's not done in detail here. If you're confused on this, I would go back to rational inequalities, okay, which was from a couple weeks back. And what you need to do for this one is you need to find the values of your numerator that make it 0, the values of the denominator that make it 0, and then create a number line where you separate the number line by those values, and then use test points. Okay, but if that sounds not familiar to you, I would make sure that you go back and watch the video that talked about solving rational and polynomial inequalities. So for this one, you get a solution of negative infinity to negative 3, and then we have this union symbol, and 1 to infinity. And then if we look here, we would set absolute value of x minus 1 greater than 0. Well, hopefully you recall that the absolute value function is never going to be negative. So the domain is always going to be all real numbers except the one when x minus 1 is equal to 0. Because if you have x minus 1 equal to 0, then we're going to have log base 2 of 0. We cannot have log of 0, so that is not going to work. So we're just going to have to exclude the number 1. So in interval notation, we're going to have an interval from negative infinity up to 1, and then a union symbol, and then 1 to infinity, but we never actually include the number 1. Because if we include 1, if we actually plug it in here, we're going to get 0, which is not allowed. Okay, now the next thing we're going to look at is the actual graph of a logarithmic function. So if we look here, hopefully recall when a is between 0 and 1, this blue graph, this should look familiar. This is your y equals a to the x power. This is your exponential graph, okay? It's decreasing, it goes through 0, 1, goes through some points over here, and it's just this nice little decreasing arch. And then hopefully remember when you graph the inverse, you can draw the line y equals x, okay? And then you can just take your original graph and flip it around that line. So if we take this blue graph and we flip it around the line y equals x, we're going to end up with this pink graph here, okay? And that's going to be what y equals log base a of x actually looks like when you have a between 0 and 1. Now if we look over here, we have kind of a similar situation, except here we have a is greater than 1. So hopefully, again, this blue graph should look familiar. This is the equation, or the graph of the equation y equals a to the x power. Again, it goes through 0, 1, but this one is increasing. And then if you draw the line y equals x, if you take this and you flip this around this line, you're going to end up with this pink line here. And again, we have an increasing function, just like this one was. But it's kind of flipped around a different way. And this one goes through point 1, 0 instead of 0, 1. So you'll notice that both of our logarithmic equations are very similar. They both go through 1, 0. This one, though, is decreasing when we have a between 0 and 1. And this one over here, when we have a is greater than 1, is going to be an increasing function. Okay, so if we take a look at some kind of more specific ones, we would have some actual points. You can notice that if you have y equals 2 to the x power, you know it's going to look something like this. It's going to go through 0, 1. If you plug negative 1 in, you're going to get 1/2 out. If you plug a positive 1 in, you're just going to get 2 out. So that would be this blue graph here. And then if we take the actual inverse of this, it's y equals log base 2 of x. And it's going to look very similar. Again, we can just flip it around the line y equals x. It's going to go through 1, 0. Instead of going through 1, 2, it's going to go through 2, 1. And instead of going through negative 1, 1/2, it's going to go through 1/2, negative 1. Because if you remember, all you have to do when you're graphing the inverse is just flip the x and y coordinates. Because that's essentially what the inverse is. It's interchanging x and y. And then if you take a look at an example over here where we have y equals 1/3 to the x power, that's our blue graph. This one we should already be familiar with. And then if we want to get the graph of the equation y equals log base 1/3 of x, it's going to look very similar, except it's just going to be flipped around the line y equals x. So here's a whole nice little list of the properties of logarithmic functions. Let's just go through these. We've talked about a lot of them already, but the domain is going to be the set of positive real numbers, meaning that x has to be greater than 0, and we did find the domain for some kind of specific logarithmic functions. The range is going to be the set of all real numbers. All right, so domain has to be positive real numbers, range is going to be all real numbers. The x-intercept is going to be at 1, and there is not a y-intercept. The y-axis is going to be a vertical asymptote of the graph. The function is going to be decreasing if a is between 0 and 1, and it's going to be increasing if a is greater than 1. And then it's always going to contain the following points. It's going to contain 1, 0, a, 1, and 1 over a, negative 1. Now, this is true if no shifting is done, but once we have some shifting, that's going to kind of change where our graph might start, okay? And then the graph is also going to be smooth and continuous. It's not going to have any corners or gaps. Okay, now at this point, we want to introduce what the natural logarithmic function is, okay? So if you have y equals ln of x, that just means, this stands for log natural, okay? That means that x equals e to the y power. So this is just a very specific type of logarithm that's typically denoted a kind of different way. So if we take a look at this blue graph here, we had looked at this I think last week, it's y equals e to the x power. This one's just increasing, it goes through 0, 1. If we plug some extra points in, if you plug e to the first power in, you're going to get 2.72. The thing to remember about e is just, it's another number, it's kind of like pi, it's going to be an irrational number. But it's not really particularly scary or anything like that. Your calculator will deal with it for you. So you just get this blue increasing graph right here. And then if you look at this pink graph here, this is the equation y equals ln of x. So instead of having an asymptote at y equals 0, this one's now going to have an asymptote at x equals 0. And this one's also going to be increasing, just like the other one was. But we have to interchange our x's and our y's, so we get 1, 0, and 2.721 as some of our points, okay? And this, instead of writing it as y equals log base e of x, log base e is typically denoted with just ln. This is kind of a nice little shortcut because we use it very, very often, okay? So log base e is just the same thing as natural log. Okay, so let's do an example where we actually graph a logarithmic function and its inverse. So let's start with finding the domain of this logarithmic function here. F of x equals negative ln of x minus 2. So for this one, we know that we have to have from 2 to infinity, because anything that's going to be less than 2 is going to give us a negative number. And if we have 2, if we plug 2 in, we're just going to get ln of 0, which is also no good. So let me back up my graphs for 1 minute. So we're going to start with kind of the typical graph of ln of x, okay, which is just going to go through points 1, 0, E1, okay, which is about 2.72, and 1 over E negative 1. So it's going to look something like this. And then we have an asymptote going through x equals 0. And then if you look here, we've multiplied by negative 1 because we have this negative out front here. So all we've done is we've taken this and we've flipped it around our x-axis. So everything has kind of flipped around. So this is now a decreasing function. And then in replace of x, we put an x minus 2. So that means that we've shifted it to the right by 2 units. So if you take a look here, we have a point at 3, 0, okay, and we also have a point at 1 over e plus 2, okay, so it's a little bit more than 2, comma 1, all right, and our asymptote has moved to x equals 2, okay, so if you look, our asymptote used to be at x equals 0, it's now shifted over to x equals 2, so this kind of reflects how our domain has changed as well. So if we take a look back at what we thought our domain was, we thought our domain should be from 2 to infinity, not inclusive of 2. And if you actually take a look at that, that's what's going to happen. You're going to have a domain going from 2 all the way up to infinity, but you have an actual asymptote at 2, so you do not include the number 2. Okay, so let's look at this common logarithmic function, all right? So we have y equals log of x if and only if x equals 10 to the y power. So the important thing to keep in mind here is that if you see a log without any kind of base attached here, the default is going to be that this base is actually a 10. So if you just plug this into your calculator, if you just do log of 5, it's going to do log base 10 of 5, okay? So base 10 is just kind of assumed unless shown otherwise. So let's take a look at this one. We have 3 times log of x minus 1. So let's just start with log of x, which is going to look something like this. You're going to have an asymptote at x equals 0. It's going to go through points 1, 0, 10, 1. So we have something that's increasing here. And then if you look at the shifting that's done, we've replaced x with an x minus 1, so that means that we should horizontally shift to the right. And you'll notice that all of our points move as well as the asymptote. So x equals 0 is no longer the asymptote, it's going to move to x equals 1. And then all of our points have just shifted a little bit. And then we've multiplied by 3. That means that we have a vertical stretch by a factor of 3. So all of our points have vertically stretched by 3. So it still goes through 0.20, but now instead of going through 11, 1, it's going to go through 11, 3. Okay, let's take a look at this. So we have our equation in blue here, 3 log of x minus 1. Okay, and if we actually look at the inverse, that's going to be given in green. So we're going to have f inverse of x equals 10 to the x over third power. Okay, so x times the 1/3 power, or x over 3, plus 1. Okay, so that would be our inverse function. And then if we looked at kind of the domains and the ranges, so for this blue function here, the domain is going to be from 1 to infinity, not including 1. Okay, and if we look at the range of the green graph, that's also going to be from 1 to infinity, not including 1. And then the range for the blue graph is going to be all real numbers. And the domain for the green graph is going to be all real numbers. So again, you can see that domain and range in this case are going to flip-flop because we have inverses. Okay, now one major thing in this section is actually solving logarithmic equations. So let's take a look at this right here. So we have log base 2 of 2x plus 1 equals 3. So we want to actually solve this logarithmic equation. So if you take a look at this, this isn't really something that we know how to deal with. So what we need to do is we need to change it so that it is exponential, okay? And once we've changed it to be exponential, then hopefully we can figure out how to actually solve it. So if we have this here, all we need to do is we need to rewrite it in exponential form. So in order to do that, we're going to take our base, which is our 2, raise it to this third power here, and say that it equals 2x plus 1. So this is that same thing that I had you write on your paper that I said you were going to be using a lot, okay? So if you rewrite this, you're going to get 2 cubed equals 2x plus 1. And then 2 cubed is just 8, so we just have 8 equals 2x plus 1. And then we subtract 1 and divide by 2, so we get x equals 7 halves. Now you always want to go ahead and check it, okay? It's really, really important with logarithmic equations because you will get solutions that do not actually work when you plug them in because of the fact that we have a restricted domain. So if we plug this in, we have log base 2 of 2 times 7 over 2 plus 1. We're going to get log base 2 of 8, which is just 3. So there's no issue here, okay? When we plug this in, this one actually works. You just need to make sure that when you plug it in, you do not get any negative numbers or 0. Okay, this one right here, I want you to take a minute and rewrite log base x of 343 equals 3. I want you to write it in exponential form, okay? And once you've written it in exponential form, I want you to see if you can figure out how to solve it. So let me give you about 30 seconds to try that. Okay, so hopefully you were able to change this into x to the third power equals 343. So this x right here is your base, this 3 is going to be your exponent. And then 343, this is a pretty large number, but we can change this, okay, into 7 to the third power, okay? So if you think about this one, probably the easiest way to think about it is to go ahead and take cube root of both sides. So you can take cube root in your calculator of 343, and you should just get x equals 7 for this one. And if we check it, log base 7 of 343, that is going to give us 3, because we know that 7 to the third power is going to be 343. Okay, let's take a look at this one right here. We have 2e to the 3x equals 6. Okay, so for this one, we actually want to change it around a little bit. Okay, we want to isolate the exponential first. So we want to get the e by itself. Okay, so we have e to the 3x equals 2 because we just, or sorry, equals 3 because we divided both sides by 2. And then we change it to logarithmic form. Now, anytime you have e, you can change it to ln. Okay, so we're going to have ln of 3 equals our exponent, which is 3x, okay? Because this is really just log base e. So this base right here is going to be log base e, which we just rewrite as ln. So we have ln of 3 equals 3x, and then we just divide both sides by 3. So we get x equals ln of 3 over 3. This would be your exact solution. So if MyMathLab is asking for an exact solution, it's going to be this right here. And then if you want an approximate solution, you just need to plug this into your calculator. So you're going to do ln of 3, you're going to hit enter or equals, and then you're going to divide that number by 3, and you should get 0.366. That would be your approximate solution. And then you would also want to make sure that you actually check this by plugging it in to make sure that it works. Okay, let's take a look at an application problem, okay? So blood alcohol concentration is a measure of the amount of alcohol in a person's bloodstream. A BAC of 0.04% means that a person has 4 parts of alcohol per 10,000 parts of blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. So for an example, if an if an individual with a BAC of 0.02% is 1.4 times as likely to have a car accident as an individual that hasn't been drinking, the relative risk is going to be 1.4%, or sorry, just 1.4. The recent medical research suggests that the relative risk R of having an accident while driving a car can be modeled by this following equation. R equals e to the kx, where x is the percent of concentration of alcohol in the bloodstream and k is going to be some constant. So research indicates that the relative risk of a person having an accident with a BAC of 0.02% is going to be 1.4. So we want to actually find k in our equation. So what we're going to do is we're going to plug in what we know. Our relative risk is going to be 1.4. So in place of r, we actually put the 1.4. And then we have e to the k times 0.02 because that is our x value. That's going to be the percent concentration. And if we rewrite this so that we have a logarithmic equation, it's going to be 0.02k equals ln of 1.4. And then if we divide both sides by 0.02, we have an exact answer of k equals ln of 1.4 divided by 0.02, which is going to give us an approximate answer of 16.82. So that would be our k value. Now, using this value of k, we want to know what is the relative risk if the concentration is 0.17%. So what we do is we are solving for r, and we plug everything in. So we have r equals e to the k, which was 16.82, times 0.17, because that is our percentage of alcohol concentration, and we get 17.5. So that means that a concentration of alcohol in the blood of 0.17%, the relative risk is going to be 17.5. So that means that a person with a BAC of 0.17% is going to be 17.5 times as likely to have a car accident as a person with no alcohol in their bloodstream at all. Now, using this same value of k, what BAC corresponds to a relative risk of 100? So now we're going to plug 100 in for the relative risk, and we're going to solve for x, which is the percent of concentration. And we go ahead and we change this to logarithmic equation. So we're going to have 16.82x equals ln of 100. And then we divide, and we get x equals ln of 100 over 16.82, which is approximately 0.27. So it means that if you have a concentration of alcohol in your blood of 0.27%, the relative risk of an accident is going to be 100. Now, let's say that the law asserts that anyone with a relative risk of 5 or more should not have driving privileges, and we want to know what should be the concentration of alcohol that should serve as kind of our benchmark for charging someone with a DUI. So if we plug 5 in for our relative risk and we solve for x, which is the concentration, we change it to logarithmic again, and we get 16.82x equals ln of 5. This is just changing from exponential into logarithmic, but please keep in mind that ln is just log base e. And we get x equals ln of 5 over 16.82, which gives you 0.096. So that means that a driver with a blood alcohol concentration of 0.096% or more should be arrested and charged with a DUI if we're interested in charging anyone with a DUI who has a relative risk of 5 or more. Okay, so let's look at this nice little summary here where we have the properties of a logarithmic function. We have our nice little logarithm right here where we have a is greater than 1. This one's going to be increasing. Domain is 0 to infinity. Range is all real numbers. X-intercept is 1. We don't have any y-intercepts. And we have a vertical asymptote at x equals 0. And then again, this is increasing. And this corresponds with x equals a to the y power. Now we have kind of the same exact thing here, except this one's decreasing, has the same x-intercept, same asymptote, and same domain as well, but the main difference here is that this is decreasing because a is between 0 and 1. Okay, now let's take a look at section 6.5, which talks about the properties of logarithms. So we're going to first work with the properties of logarithms. So let's establish a couple of properties. So let's show that log base a of 1 equals 0, and that log base a of a equals 1. So these are a couple of properties that exist, but we can actually establish these using our exponentials, okay? So if we say that y equals log base a of 1, we can change this to exponential by saying that a to the y power equals 1. And if we rewrite this, we know that we can rewrite 1 as a to the 0 power. So we have a to the y power equals a to the 0 power. Now that we have the same bases, we can actually just set the exponents equal to each other, and we can basically ignore our bases. So we just get y equals 0, which was exactly what we had as our actual rule. Okay, so it's not important that you understand or are able to exactly replicate this, but it's important that you actually understand how it's done. And let's try this one right here. Let's say y equals log base a of a, and we're going to change this to exponential. A to the y power equals a. And we know that a is just a to the first power, so we have a to the y equals a to the first, and we just get y equals 1, which is exactly what we had right up here. So these are the two properties that you need to know, okay? And you either need to know them or you need to make sure that you're on a formula sheet that's provided. I'm not sure if it is or not. I don't recall off the top of my head. But if you have log base a of 1, that's just going to be equal to 0. And if you have log base a of a, that's just going to be equal to 1. Okay, so let's take a look at a couple of other properties here. So in the properties given next, m and a are going to be positive real numbers. A is not equal to 1, and r is any real number, okay? The number log base a of m is going to be the exponent to which a must be raised. So let's just take a look at this right here. This is kind of confusing in words. But if we have a to the log base a of m power, if you have the same base here and the same base on your log, then all you're left with is actually just this m piece right here. And then down here, the logarithm to the base a of a raised to some power is going to be equal to that power. So if you have log base a of a to the r power, again, the base just cancels with this number right here, and that cancels kind of can be ignored, okay? And you're just left with r, all right? So if you have log base a of a to the r power, that's just going to be r. So let's actually use these properties. So if we have log base pi of pi to the third power, since we have pi and pi here, we can just ignore them and we're just left with 3 as our answer. So that's going to be our second property. And this one right here, if we have 5 to the log base 5 of the square root of 3 power, or sorry, 5 to the log base 5 of square root of 3, no power. This 5 right here and the 5 right here, those allow you to just ignore this part and you're just left with square root of 3. Now right here, if we have ln of e to the 0.35 t power, this one's just going to be property 2. And since you have log base e of e, because remember, ln can be written as log base e. So we have log base e of e to the 0.35 t power. This, based on property 2, is just going to be the 0.35 t because log base e of e is just going to be ignored, and we're just left with our exponent, just like we were right up here. So there are a couple of other kind of useful theorems that we're going to use, okay? So if we have two things that are multiplied, so if we have log base a of m times n, what you can do is you can split this into 2 and you can make it just so that it's the sum of the logs. So this is going to be log base a of m plus log base a of n. Now if we have a quotient, log base a of m over n, you can change this so that you're subtracting. So this is going to be log base a of m minus log base a of n. And then if you have this right here where we have an exponent, what you can do with your exponent is you can actually move it out front. So if you have log base a of m to the r power, we can take this r and we can just stick it out front. Okay, so this is going to be the same thing as r times log base a of m. So if you have multiplication, you change it into addition. Division, you change it into subtraction. And if you have an exponent out front, or sorry, an exponent, you can move it out front. Now, it should be not too difficult to remember. The multiplication goes with addition and division goes with subtraction because those are actually the same rules for exponents. So let's take a look here. So let's say that we want to write a logarithmic expression as the sum of logarithms. So let's say we have log base 2 of x squared times the cube root of x minus 1, where x is greater than 1. And we want to write it as the sum of logarithms, and we want to express all powers as factors. So the first thing that we do is we split our multiplication. Since we have multiplication here, we split it into addition. So this is actually going to be log base 2 of x squared plus log base 2 of cube root of x minus 1, because of this rule right here, because multiplication gets changed into addition. And then what you can do is you can take this cube root and rewrite it as a power. So this can be log base 2 of x squared plus log base 2 of x minus 1 raised to the 1/3 power instead of having a cube root here. And then what you want to do is you want to express all powers as factors. So this 1/3 is a power, so you change it so that it's a factor just by moving it right out front here. And we change this x squared into 2 times, okay, because we take this little 2 exponent and we stick it out front. So you can always take exponents and stick them right out front of your logarithms. So this is going to be 2 times log base 2 of x plus 1/3 times log base 2 of x minus 1. And that's as far as that one will go. We don't have any multiplication or division left within our logarithms, and we also don't have any exponents. Okay, let's take a look at this right here. We want to write log base 6 of x to the 4th over x squared plus 3 squared as the difference of logarithms. And again, we want to express all powers as factors. So the first thing that we have here is we have division. So we're going to split our division into subtraction. So we have log base 6 of x to the 4th minus log base 6 of x squared plus 3 squared. So we've just changed our division into subtraction. And then we rewrite our exponents as powers, we write our powers as factors. Sorry, I cannot talk this morning. This 4 is going to become a factor, so it's going to go up front. So we have 4 times log base 6 of x, and then we take this 2, which is again a power, and we rewrite it as a factor. So we take it and we stick it out front. So we have 4 times log base 6 of x minus 2 times log base 6 of x squared plus 3. All right, now let's look at one that is kind of nasty looking. All right, we have ln of x cubed times the square root of x minus 2 over x plus 1 squared. So the first thing we do is we have division here, so we want to split that into subtraction. So we have ln of x squared times the square root of x minus 2 minus ln of x plus 1 squared. And then we change this multiplication that we have right here, we change it into addition. And we rewrite, instead of having square root, you never want to write any of the roots as actual roots. You want to write them as powers, okay? So we change our square root into the 1/2 power. So we have ln of x cubed plus ln of x minus 2 to the 1/2 power minus ln of x plus 1 squared. And then we change our powers into factors. So we've rewritten this as 3 times ln of x plus 1/2 times ln of x minus 2 times ln of x plus 1. Okay, now we're going to do it the other way around. So we're going to be given some logarithmic expressions, and we want to write them as a single logarithm. So it's just moving in kind of the opposite direction. So we're going to do everything basically backwards. So if we take a look at this one right here, we have 3 times ln of 2 plus ln of x squared. First, we use property 5, and we take all of the numbers that are out front and we rewrite them as powers instead of factors. So we have ln of 2 cubed plus ln of x squared. And then we just go ahead and rewrite our addition as multiplication. This is property 3. So this 2 cubed is just going to be 8. So we have 8 times x squared. So we're left with ln of 8x squared. Now this one right here, we're going to rewrite our factors as powers. So we have log base a of 4 to the 1/2 power minus log base a of 5 squared. And then if we rewrite this, 4 to the 1/2 power is just going to be 2. 5 squared is just 25. And then since we have subtraction here, we just rewrite it as division. So this is going to be log base a of 2 over 25. Now I want to give you a chance to actually try a little bit of this, so go ahead and get started on part C. We're going to do it all together in just a minute, but let me give you a little bit of time to start on that. Okay, so hopefully you rewrote this so that these numbers out front are exponents. That should be the first step. So you should start by taking the numbers that are out front, those are your factors, and rewriting them as powers. So we should have log base a of 3 to the negative second power plus log base a of 2 cubed minus log base a of x squared plus 1. And then hopefully you went ahead and changed this addition right here into multiplication. So really you have 2 cubed times 3 to the negative second power. And then you still have this minus part over here. So you're still subtracting the same thing. And then we rewrote this a little better. Okay, so if you think about 2 cubed, you know that's going to be 8. 3 to the negative second power is going to be 1 over 9. So instead of writing it as 8 over 9 in the numerator, since that's not very nice, we take the 9 and we actually move it to the denominator here. And then this part becomes part of our denominator, the x squared plus 1, because of the fact that we're subtracting here. So the second part goes in the denominator, and this part right here stays in your numerator. Okay, now these properties actually help you solve logarithmic equations. So if m is equal to n, then if we have log base a of m, that's going to be the same thing as log base a of n. And this also works the other way around. So if you have log base a and log base a, they're the same bases, and you have different numbers here. Okay, let's say you have an x attached to one of them and an actual number attached to the other. What you can actually do is you can drop the log piece and just set m equal to n. So let's take a look at some examples here of approximating logarithms when the base is neither 10 or e. So let's say we want to approximate log base 3 of 12. So for this one, what we would do is we'd set y equal to log base 3 of 12, and then we'd rewrite it in exponential form. So we'd have 3 to the y equals 12. And then what we can do is we can actually take a natural log of both sides. Okay, so if we take natural log of 3 to the y equals natural log of 12, this is from property 7. Remember, if you have anything, you can take natural log or log of both sides. And then anytime you have an exponent, recall that you can move that out front so that it's a factor. So we have y times ln of 3 equals ln of 12. And then we divide to get y equals ln of 12 over ln of 3. This would be an exact value, and then you can use your calculator to find the approximate value of 2.2619. Now, there is a nice little change of base formula here for when you have logarithmic expressions where you don't have a base of 10, because your calculator will do a normal log of 10, and your calculator will also do natural log, but most of the calculators that you're probably using do not do other bases. So essentially what you have to do is, if you have different bases, so if you have log base a of m, where a is some number that's not 10 or e, all you have to do is take log of m and divide it by log of a. Or you could take ln of m and divide it by ln of a. So let's take a look at this here. Let's say we have log base 5 equals 89. All we have to do for that one is take log of 89 and divide it by log of 5. So you take log of the number that's right here and divide it by log of your base. And if you do this in your calculator, you get 2.7889. Or alternatively, you can use ln. So you could do ln of 89 and ln of 5, and you would get the same solution right here. Now, it doesn't matter if you choose to use log or natural log, as long as you're consistent. Okay, so if you use log for the numerator, you have to use log for the denominator. If you use just natural log for the numerator, you have to use natural log for the denominator. And then let's take a look at b here. This one is not particularly nice, but we have log of the square root of 5 over log of the square root of 2, and that, when you actually do it in your calculator, is going to be 2.3219, Or alternatively, you can use ln. So you could do ln of square root of 5 divided by ln of square root of 2. So just keep in mind that when you have some base here that's not a 10 or an e, you can still use your calculator to solve it. You have to just do log of the first number right here, okay, your larger number. And by larger, I mean larger physically, not larger necessarily numerically. Okay, so the one that's not a base, and then you divide that by log of the base. So here's a nice little summary of the properties of logarithms. I would make sure that you find this in your textbook and maybe make a photocopy of it or make your own copy of handwritten formulas, because these you're going to be using a lot, okay? A lot. So it's important that you actually know how to use these. I'm going to point out kind of the most important ones. This one right here, where you take your power and you move it so that it's a factor, that one is used a lot, okay? In addition, the multiplication and division ones are really important. Those are used many, many times. Change of base formula is really important. And then it's also important that you know that if you have log base A and log base A, and these are different here, you have m and n, that you can drop the log base A's and just be left with the m equals n portion. Okay, so the last section for this week is going to be section 6.6, which is kind of a continuation. This is logarithmic and exponential equations, and basically what we're going to do is just solve them, okay? So let's say we have log base 3 of 4 equals 2 times log base 3 of x. So if you take a look at this one, the first thing that we can do is we can take this factor that's out front and we can move it so that it's an exponent. So we have log base 3 of 4 equals log base 3 of x squared. This is because of this rule right here, where we're able to take an exponent and make it a factor, or the other way around. And then if you notice, we have log base 3 and log base 3. Since we have log base 3 and log base 3, we can essentially just ignore our logs and just be left with the other piece. So we just have 4 equals x squared. And then we go ahead and solve this. We get x equals 2 or x equals negative 2. Now a reminder down here, the domain of logarithmic functions is positive numbers only, so we have to check for extraneous solutions. So negative 2 is not going to work because when we plug it into the original, we're going to get log base 3 of negative 2. We cannot have log of a negative number, so this one is not going to be okay. So we're just left with x equals 2 for our solution. All right, let's look at this one here. Log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. We can go ahead and change, since we have addition right here, we can change this into multiplication. So we have log base 2 of x plus 2 times 1 minus x equals 1. So all we've done is we've changed the addition into multiplication. And then we can change this into exponential form. So this is going to be 2 to the first power, or just 2, equals x plus 2 times 1 minus x. And now we have something that's just going to be quadratic. If we go ahead and we use FOIL, and we get everything so it's on the same side, we're going to get x squared plus x equals 0. We can factor that into x times x plus 1 equals 0. And we get two solutions, x equals 0, x equals negative 1. Now we need to plug these in to make sure that they're okay. So if we plug 0 in, we get 0 plus 2, which is 2. That's a positive number, so that's good. And if we plug it in here as well, we get 1 minus 0, which is 1, which is also good. And if we plug negative 1 in, negative 1 plus 2 is going to give you 1, which is fine. And 1 minus negative 1 gives you 2, which is also fine. So both solutions are within the domain, so there aren't any issues there. So it's okay to have a solution that is negative as long as when you plug it into your logarithmic equation, you don't have any negatives there. Excuse me, I'm sorry about that. Okay, now let's solve some exponential equations. Now, it's important that you know that if you have a to the u power equal to a to the v power, then you can, again, kind of like the logarithms, you can ignore the bases here and just say that u equals v. So let's say we have something like this, 3 to the x power equals 7. So what we need to do is we need to take natural log of both sides, and what that actually allows us to do is get this x out of the exponent. So anytime you have an x in the exponent that you can't figure out how to get out of the exponent, you're going to go ahead and take log or natural log of both sides in order to help you. So we've taken natural log of both sides. It would be fine to take log as well. And then we take our x, which is in our exponent, and we just move it so that it's a factor instead of a power. So we have x times ln of 3 equals ln of 7, and then we just divide. So we have x equals ln of 7 over ln of 3. That would be your exact solution. And then the approximate solution would be 1.771. All right, let's take a look at this one right here. We have 5 times 2 to the x power equals 3. This one, you need to get the exponential piece by itself first, so we need to divide. So we get 2 to the x power equals 3/5. And then again, this looks very similar to the last one. We can take natural log of both sides, or we could take log, and then we can move our exponent out front. So we have x times ln of 2 equals ln of 3/5. So our exact solution is going to be ln of 3/5 divided by ln of 2, and our approximate solution is going to be negative 0.737. Now, these, I didn't point it out on the last one, but these should be really easy to check. If you take negative 0.737 and you plug it into your original equation, if you plug it into just the left-hand side, if you do 5 times 2 to the negative 0.737 power, you should get something that's pretty close to 3 here. All right, and let's take a look at one that's a little bit nastier looking. So we have 2 to the x minus 1 power equals 5 to the 2x plus 3 power. So for this one, we have to use log or natural log in order to get those x's out of the exponent. So we're going to just take natural log on both sides. There's not really a reason to do one or the other, except that if you have an e, you definitely want to be using natural log. So if you just always use natural log, that is kind of easiest. But if you do have a base of 10, then log is going to be slightly nicer. So if we take natural log of both sides, that's kind of our first step. And then we want to take our exponents and move them out front. Now make sure we have x minus 1 as our exponent. That's all kind of a package deal, so we need to put it in parentheses. So we're left with x minus 1 times ln of 2 equals 2x plus 3 times ln of 5. And then we go ahead and distribute everything through. So just keep in mind that ln of 2 and ln of 5 are just numbers, okay? There's nothing particularly fancy about them. You could treat them the same way that you would treat a 2 and a 5, for example. So if we distribute this ln of 2 through, we get x times ln of 2 minus ln of 2 equals 2x times ln of 5 plus 3 times ln of 5. And then when you have something like this, you always want to get it so that all of your x's are on one side and everything else is on the other side. So we've moved all of our x's so that they're on the left-hand side. So we have x ln of 2 minus 2x ln of 5. And then we've moved this ln2 that was negative, and we've moved it over here. It's now positive. So we have 3 ln 5 plus ln2. So you'll notice that everything that's on the left is attached to an x. Everything that's on the right is not attached to an x, which is exactly what you want to have happen, because then what you can do on the left-hand side is you can actually take out an x. So if you factor out an x, you're left with x times ln of 2 minus 2 ln 5 equals 3 ln 5 plus ln2, and then we just divide. So we get x equals ln of 5 plus ln of 2 over ln of 2 minus 2 ln 5, which obviously does not look very nice, but that gives you an exact solution of negative 2.186. All right, now let's take a look at something that it's in quadratic form. So we have 9 to the x power minus 3 to the x power minus 6 equals 0. So it's important to note that 9 to the x power is just going to be 3 to the x power squared. So this means that the equation is actually in quadratic form. So what we're going to do is we're going to let u equal 3 to the x power, which would mean that u squared would be 9 to the x power. So instead of 9 to the x power, we have u squared. Instead of 3 to the x power, we just have u, and then we just have minus 6. So this one you can factor. It's going to factor into u minus 3 times u plus 2. And then we just solve it. You get u equals 3 or u equals negative 2. And then all you need to do is you need to plug that back into your original substitution here. So we know that u equals 3 to the x power. So if u equals 3, I would have 3 equals 3 to the x power. Or I'd have negative 2 equals 3 to the x power. And this one's not going to work because 3 to the x is going to be greater than 0 for all x's. So I'm just going to have 3 to the x equals 3. And if you think about that, if 3 to the x equals 3, then x has to equal 1.